Welcome back, friends. Today we will discuss bent rule. Bent rule actually describes and explains the relationship between orbital hybridization of the central atom and the electronegativity of the substituent. It states that more electronegative atom prefers to stay in orbitals of the central atom having less S-character or more P-character, and lone pair or less electronegative atom or electropositive atom prefers to stay in orbitals of central atom having more S character or less P character. So to explain Bend's rule, we take trigonal bipyramidal geometry. For trigonal bipyramidal geometry, more electronegative atom prefers to stay on the axial positions. You know, these are axial bonds. And these are equatorial bonds. Now, more electronegative atom prefers to stay in the axial positions and less electronegative atom or lone pair prefers to stay in the equatorial position. Why is it so? Because it is believed that in trigonal bipyramidal, hybridization is sp3d. It is divided into two parts, sp2 plus pd. In sp2 there is s orbital and px py, and in pd there is pz and dz square. This sp2 is in the equatorial bonds and pz dz square, pd is in the axial bonds. So this is the case of unequal hybridization. That means it is a case of failure of hybridization. And you know, hybridization is a theoretical concept just given to explain geometry of the molecule, arrangement of the orbitals. But here you can see in equatorial bonds S character is more, and in axial bonds there is no S character. More electronegative atom prefers to stay in orbitals having less S character. That's why axial positions are occupied by more electronegative atoms and equatorial positions are occupied by less electronegative atoms or electropositive atoms or lone pairs. Because if S character is more, then electron density is closer to the central atom, and that is the case when less electronegative atom is attached, and if it is lone pair, electron density is on the central atom only. But if more electronegative atom is there, then it withdraws the electrons from the central atom, and it is possible only if central atom orbital involved in this bonding has less S character, or we can say more P character or D character. Let us take example of PCL2F3. We have PCL2F3. Now, if it is PCL5, all the positions are occupied by chlorine. There is no such case arises. But now we have two different atoms. So fluorine prefers which position? These are equatorial position, axial positions. So axial positions are occupied by more electronegative atom. That means fluorines are on axial positions, and one left, that is on equatorial. Chlorine are always on equatorial position. Now, axial bonds are longer than equatorial, but it is only possible when all the atoms are same. Now you can see axial bonds are longer than equatorial bonds. So DPF axial is greater than DPF equatorial. But what about PCl? Chlorine is larger in size than that of fluorine. So D of PCl equatorial is larger in size than even DPF axial. That means if atoms are different, maybe equatorial bond is larger than axial bond, but axial orbital length is always greater than equatorial orbital length. Let's take another example. So let us consider these three examples. In first case, phosphorus has 5 bond pairs, 2 CH3 are attached and 3 CF3. So now we consider group electronegativity. So group electronegativity of CF3 is greater than CH3. So out of these 5, which one are at axial position first? As we discussed earlier, axial positions are occupied by more electronegative substituents. So out of CH3 and CF3, which one is more electronegative? CF3, because fluorine is more electronegative. That's why CF3 groups occupy axial positions. CH3 groups and one of the CF3 will occupy equatorial positions. So why CF3 are at axial positions? Because they are more electronegative substituents, and more electronegative substituents prefer the position which has less S-character, because if less S-character is less, electron can be easily moved away from the central atom. Right? Now come to SF3Cl. In SF3Cl, there are 4 bond pairs. And how many lone pairs? Sulfur has 6 electrons. Out of 6, 4 are used. So how many left? 2, means 1 lone pair. Total 5. Arrangement is trigonal, bi-pyramidal. These are the positions. So out of these positions, axial positions are occupied by more electronegative atoms, and equatorial positions are occupied by less electronegative, electropositive or lone pair. Lone pair is just like that very less electronegative atom is attached. So shared pair is towards central atom. So lone pair will occupy equatorial position, because lone pair means electron density is very close to central atom, and electron density closer to central atom means it is S rich. Orbital of the central atom is S rich, S orbital rich, or the central atom orbital is rich in S character, and remaining we left with one fluorine and one chlorine, so they will occupy equatorial positions. Come to this iodine, Cn twice negative. So there are two bond pairs. How many lone pairs? Iodine has 7 electrons, one is gained, so total 8. Out of 8, 2 are shared. So how many left? 6. So there are 3 lone pairs. 2 bond pairs, 3 lone pairs. So it can be easily predicted that lone pair will occupy equatorial position, being S rich. So lone pair are on equatorial position, and see here. So this is linear because of symmetrical arrangement of lone pairs. This one is seesaw due to the presence of one lone pair, and this is simply trigonal bipyramidal. So alternate definition of bent rule is that orbital occupying more space around the central atom will have more S character. So for trigonal bipyramidal geometry, you know, this is the case. 5 bond pairs. Now, an axial bond is in the neighborhood of 3 equatorial bonds at 90 degree. Means but equatorial bonds will have 4 neighboring orbitals, 2 at 90 degree and 2 at 120 degree. That's why equatorial bonds will occupy more space around the central atom than that of axial bond. That's why equatorial bonds will have more S character, and so is the unequal hybridization. So these equatorial bonds are sp2 hybridized and axial bonds are pd hybridized. That means on axial bond S character is minimum, or we can say no S character, but in equatorial bonds there is 33.3% S character. So this is the alternate definition to Bendt's rule. For pentagonal bipyramidal geometry, you know, atom five bonds are in plane at 72 degree and one above the plane, other below the plane. So now these axial bonds has axial bonds have 5 neighboring bonds at 90 degree, and equatorial bonds have how many neighboring? Suppose this equatorial bond has 4 neighboring bonds, 2 at 90 degree and other 2 at 72 degree. So that means axial orbital occupy more space than the equatorial orbitals. That means axial orbital has more S-character. So if there are lone pairs, they will prefer to occupy axial positions in pentagonal bi-pyramidal geometry, and that will explain the structure of XCF5 negative. So in XCF5 negative, there are 5 bond pairs. Xenon has 8 electrons plus 1, 9. Out of 9, 5 are shared. So how many left? 4. So 2 lone pairs. So there are 5 bond pairs, 2 lone pairs. That's why XCF5 has structure like this. These are 5 fluorines on the equatorial positions and 2 lone pairs on the axial positions. So band rule successfully explain the structure of XCF5 negative. So band rule can be used to explain the bond lengths. Like we have example of CH3F, CH2F2, CH3 and CF4. So in first case we have only 1 CF bond and 3 CH bond, and you know fluorine is more electronegative and hydrogen atoms less electronegative. So S character, you know, in CH, as hydrogen is less electronegative, so electron density is closer to carbon, and in fluorine is more electronegative, so electron density is towards fluorine. So this orbital of central atom has less S character than these 3. So that means S character is more in CH bonds. Though it is sp3 hybridized, but S character is not 25% in all of these. You know, in sp3, what we do? Percentage of S character is, S is 1, total 4 into 100, so 25%. But it is not so in this case because they are of different electronegativity. So S character is more in CH, more in the orbitals attached to hydrogen than the fluorine. That's why as S character is less, so bond length is more. Come to this part. Now we have only 2 CH. So contribution of S towards hydrogen is less, and towards fluorine it increase to some extent. That's why bond length decreases. Same next, there is only one hydrogen, so S character towards hydrogen decreases and in CF bonds increases, so bond length decreases, because as S character increases, bond length decreases. And in case of CF4, all of them have 25% S character, and that's why bond length is minimum, because here percentage of S character is maximum. So as we go this along the series, percentage of S character increases and bond length decreases. So in this way, Bent rule is used to explain the average CF bond length in these molecules. We can say bond length is inversely proportional to percentage of S character. Bent rule can be used to explain the bond angle. So you know, if you see in ethane, ethene, ethyne, so ethane hybridization is sp3, in ethene hybridization is sp2, and in ethyne hybridization is sp. So for sp3, bond angle is 109 degree 28 minute. sp2 bond angle is 120, and in sp bond angle is 180. So in sp3, percentage of S character is 25%. In sp2, percentage of S character is 33.3%. In sp, percentage of S character is 50%. You know, there are two, one S, one P, so 1 by 2 into 100. So as percentage of S character increases, bond angle increases. That means if in bonding orbitals percentage of S character is more, bond angle is on higher end or higher side, and if percentage of S character is less, then bond angle is low. Now come to this. In Bent's original paper, methyl is considered as less electronegative than hydrogen. Why is it so? Because he considered its group electronegativity, and you know, methyl decreases the acidic character of carboxylic acids. If we compare formic acid and acetic acid, formic acid is stronger acid than acetic acid, because in formic acid hydrogen is there, in acetic acid methyl. So methyl is electron releasing group. So he considered group electronegativity of methyl as less than hydrogen. So as methyl is less electronegative, so its orbital has more S character. According to the statement of Bent's rule, less electronegative atom prefers orbitals having more S character. So that means S character of these bonding orbital is more, and that's why bond angle is on the higher side, 111 degree. Only one methyl, so percentage of S character, because on one side there is hydrogen, so percentage of S character is less, so bond angle is decreased. In hydrogen, further decreased. You know, fluorine, it is more electronegative, so more electronegative atom prefers orbitals having less S character, and that's why percentage of S character is less, so bond angle is on the lower side. So in this way we can say bond angle is proportional to percentage of S character, and it is inversely proportional to electronegativity of substituent atom. So as electronegativity increases, bond angle decreases, because as electronegativity increases, percentage of S character in the orbitals decreases, because bonding electrons are more towards more electronegative atom, and that's why which orbitals are favorable? Which has less S character, and so bond angle decreases. This example is given in Inorganic Chemistry by J.E. Hui. So see, this phosphorus formed 4 sigma bonds and 1 pi bond. So phosphorus is approximately sp3 hybridized. Now, as phosphorus is attached to 3 oxygens and 1 bromine, oxygen is more electronegative, because according to Bent rule, more electronegative atom prefers to stay in orbitals having less S character. So as per expectation, these oxygens which are singly bonded to phosphorus has around 25% S character. Now this oxygen, exocyclic oxygen, it is also expected to have less than 25% S character, but surprisingly this bromine, out of these 4, bromine is least electronegative. So this bromine being less electronegative, according to Bent rule, it prefers to stay in orbitals having more S character. But surprisingly, boron also attract less than 25% S character. The only this oxygen, exocyclic oxygen, attract only exocyclic oxygen attract 40% S character. So why is it so? All the oxygens have almost same electronegativity. So why these oxygens attract only 20% S character of the hybridized orbital? Bromine even less electronegative but attract less than 25% S character. But this exocyclic oxygen attracts 40% S character. Reason lies in the overlap. Bromine, first reason is bromine is large in size, it has diffused orbitals, so bonding is weak. And second reason is phosphorus attached to this oxygen has pi bond in addition to sigma bond, so this bond is strong. This oxygen comes closer to the phosphorus, and because of this bond strength, it attracts around 40% S character, which was not explained by Bent. So Bent rule might be restated as P character tends to concentrate in orbitals having weak covalency, either electronegativity or overlap consideration, and S character tends to concentrate in orbitals having strong covalency, match electronegativity or overlap. This argument is supported by the bond energies. For example, if we compare bond energies of phosphorus bromine, phosphorus oxygen and phosphorus double bond oxygen, phosphorus bromine has only bond energy of 264 kilojoule per mole. The single bond O is 335 kilojoule per mole and P double bond O, it is 544 kilojoule per mole. As phosphorus double bond oxygen has maximum strength, it's good overlap, that's why it has maximum S character. Here it is 335, so it has almost 20, it has 40% S character. In this case, it has 25% S character and it has less than 20% S character because of bond energies, or we can say overlap. It has maximum overlap and it has minimum overlap. So as it has minimum overlap, it has least percentage of S character, maximum overlap, so it has maximum S character. This is all about bend rule. Thank you very much for watching this video. Do like, subscribe and share my channel. God bless you all. Happy learning.